All right. So as I mentioned, welcome to our week 5 of our Intro to Cybersecurity series. We'll go ahead and get started here. And the main topic for this week will be cryptography. So cryptography, this focuses on the confidentiality part of the CIA triad. With that being said, of course, we want the receiver to be the only one to see our messages. So of course, confidentiality, as mentioned, as you can see here, sender encrypts the message and the receiver decrypts the message. Of course, cryptography is the practice of techniques for securing communication, whether that be data in motion or at rest. Of course, in motion through the internet, as we mentioned prior, the internet was meant for communication, but was not built on a security basis for it. So we do have to implement cryptography and other encryption techniques so our messages get to people who it's intended to reach. With that, we use a combination of confusion and diffusion. We'll go over that in a little bit here. And we'll briefly cover shared and private keys. We'll wait on going into more detail on private keys for our following lecture next week. We'll also get your feedback on what you guys would like to see a bit more of once we go over today's slides. So let's see. So for confusion and diffusion. So confusion, as we see here in this little diagram, there's a difference being the basis. Confusion utilized to generate vague ciphertexts, and then diffusion utilized to generate obscure plain text. So with that being said, understanding statistical characteristics with how the alphabet works can allow an attacker to know if, like plain text, by understanding the frequency distribution of alphabets. Like in English, we utilize the letter E the most statistically. Of course, this was briefly evident in like World War II and the enemy would broadcast quote unquote encrypted messages, but with known sign-offs at the beginning and end of every message. So as long as you can understand how they end it, you can pretty much decrypt everything else. Of course, confusion seeks to make a relation between the statistics of that ciphertext and the value of the encryption key as depicted or as complicated as possible, while diffusion states there that the statistic relationship between plain text and ciphertext is made complicated. So really in layman's terms, confusion is the cryptographic technique that allows an increased vagueness of the ciphertext. So that ensures that the ciphertext gives no clue about the plain text. And this can be achieved by using substitutions, which is what we'll go over, or by scrambling algorithms that rely on keys, and of course that input text, while diffusion is a cryptographic technique that allows an increase of redundancy of the plain text to obscure the statistical structure that we mentioned before. And this helps prevent attempts to deduce the key. Some other key points here: confusion is really only with block ciphers, not stream ciphers, and diffusion is both with stream and block ciphers, which we'll go over next week. See, as I mentioned, increased vagueness for confusion, increased redundancy for diffusion. So here is a picture, the basic overview of how we get plain text from one person to another with encryption. So we have Alice and Bob. Alice wants to give Bob a message, but we don't want anyone else to see it. So Alice and Bob have a key, and this is what we call a shared key. Alice encrypts that message with her key, her shared key, sends it to Bob over any kind of medium, could be internet, could be paper, could be anything. And even if who we have here, what we call Trudy, the intruder, and even if Trudy were to have that encrypted message, if she doesn't have the key, then she can't decipher what is being said. So once the message gets over to Bob, he'll have that key and be able to decrypt it. Let's see. And on the bottom here, we have a bit of math just to show how it can be done. So M is the plain text. KA is just to signify that it's Alice's key, but this is technically a shared key. So KA and KB are the same. So KA of M is the ciphertext. And the way we get M is by canceling out the keys from K, from Bob's and Alice's key from that message, or to the message. So we'll go over that in a bit, but the main point of that, how that works is with the XOR, exclusive OR operation. As mentioned here, it's the heart of many cryptographic operations. And as we can see, and I hope I can go right. Okay, so this is just an XOR truth table. And you'll see this in your computer science classes. You'll see this in your regular math classes, hopefully, and as well as in your engineering classes. And of course, moving into the upper advanced courses like intrusion detection and advanced cryptographic algorithms course. As you can see here with our truth table, 0 and 0 is 0. 0, 1 is 1, 1, 0 is 1, 1, 1 is 0. So we can make an obvious observation that as long as the values are the same, the output will always be 0. While they are different, they'll be 1. And with that being said, brings us to our mathematical preliminaries on XOR. So we have communicative or commutative. A XOR B will still be B XOR A. It doesn't matter which order you put it in, it'll still result in the same output. All right. Number 2, we have associative. So we have A XOR B XOR C. And it doesn't matter which ones you do first, since as we mentioned before, it's a combination of 2 to get 1 output. So no matter if we do A and B or B and C first, we'll still get the same. So just as an example, so I have a black screen here. So A XOR B XOR C, and let's just say that we have 1, 0, 1. A is 1, B is 0, C is 1. And the way that we would do that is we pair them up. And so we go back to our truth table. We don't understand or don't know yet what 1 and XOR 0 is. 1 XOR 0 is 1. So we'll come back down here, 1. So now we have 1 XOR 1. Since they're the same, going back to that truth table, it's 0. And same thing as if we were to do, the other way around. Zero XOR 1 would be 1. 1 XOR 1, 0. Oh wait, excuse me. Yes. So going on to our third identity, or our third preliminary identity, A XOR 0 equals A. The way that we can explain this one is, let's say that A is 1. So 1 XOR 0 has to be 1. So if we have A is 0, then 0 XOR 0 is 0. So in the end, you'll get A XOR A, or A XOR 0 is A. Then we have the self-inverse. Self-inverse, basically, if A is 1, which means A XOR 1 XOR 1 will be 0, and 0 XOR 0 will be 0. And lastly, we have the complement. Unfortunately, with this font, it doesn't show, but there should be a not symbol above this second A. So while A is 1, not A is the opposite of that, being 0. And going back to that truth table, 1 XOR 0 is 1. The same thing if we were to have A as 0. Not A would be 1. So we have 0 XOR 1 is 1. So these are good to remember, since you will, if you take these courses in the future, you'll be tested on these, and you'll be tested a little bit on it in our homeworks that we assign for this week. Let's see, another thing that I want to get on before we continue. Right now, we've only been working with pairs of 2. I want to go ahead and ask if you guys can help solve this problem that we have. And before I continue, does anyone have any questions regarding any of these mathematical preliminaries for XOR or how XOR works? No, we'll go ahead and move on. So it may be daunting, but we'll go ahead and try this out and see where you guys land. Hopefully it's not too scary. But our first question will be solving this one. All right. So with those properties, can anyone solve this one before I go ahead and explain how it is? And I can tell you a very easy way, but I'm gonna wait for you guys to maybe give me an answer. It's either 0 or 1. Just remember the table is truth table was right. So I'll go ahead and help you out with working on it. I'll show you the long way, then I'll show you the short way. So what we can do easily is just pair each one up. Try to make sure there was an even amount, just so it's a bit easier. So 1 and 0. What is that? Okay, if we look at our truth table, that's going to be 1. We have 1. 1 and 1, that's 0. 0, 1, that'd be 1. 0, 1, 1, 1, 0, 1, and 1, 1 is 0. Okay, well now we have 6 of them. So let's pair them up again. 1, 0, that's going to be 1, 1, 1, 0, 1, 0, it's 1. And lastly, just this one, 1 and 0, that's 1. And then we just bring that one down. So lastly, we have 1 XOR 1 equals 0. So our answer is 0. And I do want to explain that there's an easier way to do this, especially if it's just at least a decent amount, a short amount of numbers. Any more and it might get a little confusing, but this number depends on the even or odd amount of ones. So we have 1, 2, 3, 4, 5, 6, 7, 8. Since it's an even amount of ones, it'll be 0 right off the bat. So that's the long and short way of solving these mathematical preliminaries. Does anyone have any questions on that? Check. Does anybody have any questions? Concerns? Because we'll soon move into to encrypt with just zeros and ones here. It'll be a short one based off of these principles here. If not, it's okay. We'll move on. Oh, we have a channel. Could you explain the short way? Oh, yes. Sorry, I already moved everything away. But let's just say, for example, where it is. Yeah. Okay. So this one, then we have okay, so these are two different ones. So as we mentioned before, if let's see, like for the self-inverse, if there's an even amount, see with the self-inverse one, it's very easy to explain. Since A and A are the same, A equals 0, because according to our truth table, same and the same equals 0, same equals 0. So going back to self-inverse, our rule number 4, A XOR A is 0. And if we decided to do A XOR A XOR the inverse of A being a not. So this would be 1, 1, 0. And if we try to do a proof on that, these two combined, 1 and 1 is 0. 0 XOR 0 is going to equal 0. So yeah, so it'll always be 0 as long as there's an even amount of ones or values there. So in this case, if we go and count the ones, there's 1, 2, 3, 4, 5, 6, 7, 8. Even amount of 8 or even amount of ones, so we have a 0. 1, 2, 3, 4, 5. Well, that's odd, so we'll give it 1. And just to show a bit of proof here on this one, I can try these up real quick. So 1 and 1, that's 0 since they're the same. 0 and 0, that's 0s. 1 and 1, that's 0. 1, 0, that's 1. 0, 0, that's 0. 0, 0, that's 0. Pair them up again. Oh, that one. This is 0. This is 1. This is 0. Pairing these. This is going to be 1. Lastly, X4. Bring that down. 0. So 1 XOR 0 is 1. So I was able to solve it without even having to do all of the proof. You're welcome. All right. Now that we've got a basic understanding of that concept, let's move on to a quick little cipher. Let's see. All right, keeping that same concept, and I'll leave the truth table up at the corner here. Let's see, it's going to be 0. All right, this is our truth table. And our message will be 0, 0, 1, 1, 0, 1, 0, 1. And I'm going to give, in this case, going back to the Alice and Bob chart that I mentioned, we're going to give it a key. And our key is going to be 1, 1, 1, 0, 0, 0, 1, 1. All right, Ramon, we'll see you next week. Now, so this is our plain text. And this is our secret key. So now we're trying to create the cipher key or ciphertext. So it may be a little bit different because we are working not linearly this way. We're going to be working up and down to solve this. So 1 and 1, that's 0. 0, 1, that's 1. And before I continue, I'm going to have the rest of you finish this and put it in the chat of what the answer is. I went ahead and did the first two, but you can start from the left and work your way to the right. I'll give you like a couple minutes to solve that one. All right, so yes, we already got some answers here. And that is correct. So if we look going right to left, at least still continuing what I said, 1, 1 is 0, 0, 1 is 1, 1, 0 is 1, oops, 1, 0, 0 is 0, 1, 0 is 1, 1, 1 is 0, 0, 1, 1, 0, 1, 1. And that's our ciphertext. So just to prove a concept, we'll bring that key back down. 1, 1, 1, 0, 0, 0, 1, 1. This is our secret key. And now we're going to find that plain text again. Same concept. 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0. And we have the same answer as we started. So this is how that shared key works on a basic level. Right. Does anyone have any questions on that? I would hope not, because I feel like I try to go as thorough as possible, but that's okay. All right, what we'll move on to now is our next slide, which will go over mod operations. Mod operations allow us to create ciphers in a way that involves confusion. So stating here, mod in means the remainder when dividing by n. So example being 20 mod 3. So basically 20 divided by 3, well, that fits into that, what is that, 6 times? So 18 with a remainder of 2. So our operation ends with 2. And keeping in mind that mod n results always between 0 and n minus 1. So you'll never see this mod 3 having a value of 3 because then it fits into that again. So let's say it was 21 mod 3. Well, 21 or 3 goes into 21 7 times, so it's 0. All right. And then of course, for the other example, 100 mod 10 divided by 10, so number So its remainder is 0. This is helpful when moving on to our next slide here. But right before that, just so you're aware, there's never negative numbers in a mod operation. So as example here, -3 mod 5, we wouldn't be able to solve for this. So we'd have to add an n number of 5s to get back to the positive. So of course, 5 plus -3 is 2. So that's why we have 2 as our answer. So with that being said, let's see. Okay, I go on to that. Let's see. All right. So just keeping this in mind for when we go over our first cipher. We'll move on though. There are 3 different types of attacks. Let's see. That would be, there it is. Yeah, so the ciphertext only, of course, hacker has a ciphertext to analyze, but nothing else. So you're just given a ciphertext and you have to solve for it. Known plain text, the attacker has a plain text corresponding to the ciphertext, basically 1-to-1. And then chosen plain text attack is when the attacker gets ciphertext for a chosen plain text. So if you were able to solve for maybe a word in the string of encrypted characters, then you can probably solve the rest of it with that last one. Does anyone have questions about the types of attacks? Or the mod operations that we went over? Now we'll be moving on real quick. This here, so this would be in relation to frequency analysis. So with like monoalphabetical substitution ciphers, much like what we mentioned in our chosen plain text, it'd be easy to show how it can be decrypted without having to do too much work. For example, the letter A in plain text will always be the letter X in the ciphertext. So since there's no offsetting after each encrypted letter, attackers can quickly see that 2 or 3 letter words or phrases will have the same repeated pattern. So that's a drawback to a cipher that only has encryption or only has cipher or shifting ciphers. With that being said, you can see how we can find related words from the encrypted message at the top left, and then using 3-letter words like B and we can quickly decipher them. With a bit of time and effort, you'll eventually come to your end result here at the bottom. This is an example of an English poem. It was solved fairly quickly, but this leads us to our first cipher being the Caesar cipher. At least the background for it. Let's see. Yeah, it's one of the simple and oldest well-known encryption techniques. It uses the substitution cipher, in which each letter in the plain text is replaced by a letter of some fixed number of positions down the alphabet. So A is always going to be 0, but you can change that, and Z will be 25. And it uses mod 26 because there's 26 letters in the alphabet. More often than not, encryption will be adding and encryption will be subtracting. You can always change it up. But in this example that I've written here, A, which is 0, plus 15, mod 26. So 0 plus 15 is 15. And since 26 can't go into 15, it's just going to equal 15. So down the line, we have 15 being P. And the same thing with T. In our second example, T is here plus 20 mod 26. So that gives us 39 mod 6. Well, at least 26 can go into 39 at least once. So finding the difference, we'll see that the encryption will be 13, which is in. So what I want to do now is give you guys an example. Noting that we have mod 20, keep in mind mod 26 for the alphabet, English alphabet at least. We're going to rotate, this is here, rotate 13 to the right. So if we're given that same example as before, A, in this case, we'll do plus 13, and then mod 26. A plus 13, well, A is 0, 13. So it's just 13 mods 26, 13 is in. So if you guys can, using this graph here on the bottom, encrypt or create a ciphertext out of crypto with the rotation of 13. I'll give you guys some time to do that. All right, do we need more time or? You race, yeah, okay. I'll wait a little bit longer. All right, so we at least have one person done. So let's go over this real quick. Okay, so since our rotation, I pressed the wrong button, sorry. Since our rotation is 13, we can use this alphabet and number table here to help us out. So we can do this as numbers. So C is 2. So 2 plus 13 is 15. So our first thing is E. R is 17. Oops, second. Is 17. And we're adding 13. And that gives us 30. But there's only up to 25. So what we do is after we reach Z, we go back to A and continue. You do it visually that way, or you can simply do the mod calculations as we said before and divide by the 26. So that should give us maybe 4, am I right? Yeah, let's just double check on that real quick. R, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. So then we have P, E, Y, same thing, 13, so 1, 2, 3, 13. So we get L. And tell me if I got that wrong. But T, E, C, E, then lastly O. U, that's what we got? Okay, yes. And Orlando was able to help us out and confirm that for me right away. Thank you. All right. So yeah, having the table here is kind of helpful too, because even with a calculator, you gotta do a little bit extra arithmetic to get a whole number out of it. But you'd be able to do it that way. And now we have our second one, and this is going to be decrypting. A little longer, I know. And we have a rotation of 19. So if you guys want to, give you guys 5 minutes, maybe a little less than that, since we're already at 5:45-ish. But yeah, I'll give you a couple minutes to solve this one. And remember, with decrypting, we go left, we go back, we don't go forward. And once you guys solve it, if anyone has it already solved, you can go ahead and leave it in the chat. Or just give it an extra minute if you've already done so, at least so everyone else has a chance to do so. I give it 30 more minutes before we go ahead and spill these. All right, you can go ahead and if anyone has the answer, you can put that in the chat. So my mic is open, yeah. Yes, Orlando, apparently you don't know. Just kidding. But the plain text out of this spells out, I don't know. Gotta be a little funny on that one. But I can go ahead and explain it a little bit, but I don't want to be too long. I want to make sure we are done by 6 at least. But let's see, at least with B, let's try with B. So 1, 2, 3, 4. 15, 16, 17, 18, 19. So first one is I, W. So at least 22 minus 19, 3, D, H wraps around, 7 minus that, that's 0, that's O, and G, so one more, so N. What's the next one? M, 19, no, and then of course the rest, obviously, K, N, O, W. All right. So that is the Caesar cipher shift in its simplicity. But can anyone tell me how we can maybe make this a little bit better as far as an encryption? There's at least one way to do so, which would help. And with that being said, you could simply just change the order of it. You don't have to have A through Z alphabetically. You can shuffle them around and give them different value numbers. But like we said before, with these types of ciphers, A will always be X or B will always be G, and it won't rotate. It'll just stay the same. So even with that type of cipher, shift cipher, you'll still have issues with it being solved fairly easily. So a solution to the Caesar cipher, which still keeps to the structure of it, we simply would add a key. And with that key, we have now a graph here. I don't let that be crazy, but we won't take too long on this one. But if you see that we have plain text cryptography, and we're going to use our key as luck. So we're going to combine the way that we did the encryption with the key LUCK. With that being said, let's see. So each number has its own value. So L is 11. U is 20. Actually, let me write it somewhere. L is 11. U is 20. C is 2. And K is 10. So now we have a pattern here, 11, 20, 2, 10. And yes, the key only has 4 letters, while our plain text has, well, as many as we want. So what we'll end up using or doing with this key is rotating it back to the beginning every time. So after we encrypt with LUCK, we'll do it for each letter. So C in cryptography will be paired with L for the key. R will be paired with U. Y will be paired with C. P will be paired with K. And then it repeats. So T paired with L, O, U, G, C, R, K, and then so on and so on. And this will give us a more, this will actually introduce what we discussed before, diffusion. Because before we were only working with confusion. Now we have an element here that can help us out and really include obfuscation to our cipher. Won't need to solve for this one since we don't have too much time. We might have that as a homework. But I just want to make sure you guys were aware of this one, which is a bit more involved. Takes a little bit more time. All right, does anyone have any questions on the Caesar cipher or Veneer cipher? Oh, we also have an example here for from cipher to plain text. I should say plain text. But this one's a short one, but I'll go over this one at least just so we can see. We're going backwards. So the cipher key pair. Okay, so in, start with in, and we'll use T as our key for that one. So that's 19. So we'll go left. So 18, 19. So first one is U, and then X. We'll do E, so that's 4. So it's 1, 2, 3, 4. T, X. Start at X. Wait, sorry. Oh, using X. X is 23. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 15. 17. Great. R. Let's see, G, A. So we'll start with G. And since A is 0, we'll stay there. So you kind of understand where it's going. And then N is with S. S is 18, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18. There we go. UTRGB is our plain text. And this is how the Veneer, I'm assuming I'm pronouncing that right, Veneer cipher works. Another one that we have, just to briefly go over, is I can't even pronounce it right. Not to confuse with stenography, because stenography is actually a way of typing in a court of law for vast transcriptions. But stenography has messages hidden in photographs or any text. There's also text stenography, much like you see here, with the messages being hidden in the words. Every capital letter is actually part of the secret message. Within every pixel, as you see here with the Mona Lisa, it can have a hidden message in there. And then it can happen in the hex dump file, which is a tool that you can use for digital forensics. And with that, you can even see in the header file that there's hidden messages as well. So stenography has a lot going on, just to go over briefly, but we do have an additional PowerPoint just really quickly to go over what it looks like. So we have our message file, and then the cover file. Cover file would be the one that we're putting that secret message in. Then we'll use the tool to inject it any way we want. And then of course that will be our hidden message. And then as long as they use the same signography tool, they'll receive that hidden message. This is a whole other lecture with slides on it. If you guys are interested, we can definitely go over signography a little bit more. You can see how you can detect signography with different methods. I believe this was, how was this done? It was done with encryption tool or decryption method as far as to see the signography detected, or do you remember that one? Yeah, the one where it says detecting it. Oh, I don't remember how. It's sensitive. It's the slide before. Oh, slide before. Okay. So first is like in analysis. Oh my gosh, using different tools like there is Sense Secret, Signography 8.1, Stick Attack, Inderman. Okay. Yeah, we can definitely go over this a little bit more in the future, but just to give you a brief idea of what signography is, there's even in regards to the hex number or hex value for a lot of these, even with the Mona Lisa example here, you can see through a histogram, you can see where the spikes are. So a lot of this can be hidden in photographs or through plain text as well. And then just so we can wrap it up for today, we also have Morse code, which is just a series of dots and dashes. And here you see hello UTRGV in its Morse code. Of course, we have the Morse code graph on the right. Aside from that, and then we can go back as well to the Enigma machine, which was pretty revolutionary at the time. But this machine was used in World War II by Nazi Germany military, and Marian Rejewski, which is a Polish mathematician, found flaws in the German ciphertext and to inform the British and French. Much like I said before, if you stick to the same cipher, eventually it will be solved. But during the height of the war, they went ahead and started changing it up. And that's where Alan Turing came in to invent the bomb, which of course reduced the work of what they called code breakers, which nowadays we would call hackers. So it's a very revolutionary machine, and both very, very revolutionary machines. I would recommend looking up a YouTube video on the history and the technology behind the Enigma machine, because it's very fascinating. Not only did they decide on the codes up here at the top, right here, they would change these daily, and they would also change the switchboard here daily. So even if you press the letter D several times in a row, you would have different lights flashing for different letters. So it would never be the same all the time, because when you click it down, it would go through here, then it would go through another letter, then it would come through and weave through this box here to be then scrambled again using confusion and diffusion, and then come back in a different route and then light up one of these lights. So the science behind it is very fascinating. I'd recommend you guys go and watch a YouTube video on it. There's some very good educational ones. We'll go ahead and leave like a list in the chat later or in the Discord. And aside from that, I think we're wrapping up here, because our next lecture will either go over more of these other topics that we've been over briefly. If you guys would like the history of the other ciphers and other methods, but I do want to try to get stream ciphers, block ciphers, private keys, and a little bit of DES and AES moving forward, so we can really get into cryptography. But aside from that, are there any questions for us today before we wrap up? Just take it then. Okay. If anyone needs, we can go back and explain it, but I'll go ahead and stop the recording now. So we have too long of a recording here.